This is a brand new topic. We didn't have this in the previous class, so this is new for everybody. BGP is the Border Gateway Protocol. It is used on the internet to exchange routing information between customers' networks. So when I say customers' networks, I'm talking about like AT&T, Verizon, Sprint, the internet service providers. All right, but BGP is a completely unique type of routing protocol. And you're going to see that as we go through the chapter, how different BGP is from all of your other routing protocols. First of all, BGP runs over TCP, whereas EIGRP and OSPF run right on top of IP. It is a classless protocol, but believe it or not, BGP doesn't use metrics. It uses something called path vector attributes. And we're going to look at some of those attributes in this chapter. Okay? So BGP already is very different, even with just the first couple of things we looked at. It runs over TCP. It is a path vector protocol, meaning it doesn't have any metrics. There's no cost, bandwidth doesn't come into play, delay doesn't come into play. In fact, when you look at routes in a BGP routing table, the second number in the brackets is always a 0 because there are no metrics, at least not in a traditional sense. BGP does do incremental updates, meaning that it doesn't blast out its routing information every X number of seconds. It only sends out routing updates when they occur. And it is a path vector protocol, so we have these path vector attributes that we use to manipulate how BGP decides to route. There are about 14 different path vector attributes that we're going to take a look at. Well, we won't take a look at all of them, but we're going to look at most of the popular ones. Okay? BGP is one of the most widely used protocols on the internet because it essentially interconnects all of our service providers. BGP is the protocol that builds the internet. There is no reason as a consumer that you should ever be running BGP inside of your network. It is not designed to be an interior protocol. It's not efficient enough to be an interior protocol. It's actually a very slow protocol by design because it's used in very large routing domains. We use autonomous system numbers in BGP just like EIGRP. All routers that want to communicate to each other have to have an autonomous system. But in BGP, there are actually private and public autonomous system numbers. Private autonomous system numbers you can use inside your network. Public autonomous system numbers are the ones that are used on the internet by the service providers. Okay? So BGP is what we call a path vector protocol. A path vector protocol defines a route as a pairing between a destination. The destination, of course, in this case, is the destination network, which is the same as any other routing protocol. The destination is where I want to get to. But in a regular IGP protocol, the destination is paired with what? It's paired with a metric. But in BGP, the destination is paired with path attributes. Now, I don't expect you guys to look at this table and go, gosh, I know what all that stuff is, right? AAS path, origin, metric, local preference, wait, next hop. I don't expect you guys to know what that is yet. We're going to learn what all those things are as we go through this chapter. This is an example of path attributes. This is how BGP decides what path to choose. It looks at all these characteristics of a path, and based on those numbers, it makes a decision. Again, I don't expect you to know what med is, what local preference is, what weight is, what AAS Path is. You will after the end of this chapter, but not right now. That's just up there as an example, okay? So let's talk about these attributes because the attributes are very important to understand when it comes to BGP. By the way, this BGP chapter is only in here because there's like one question on the test about BGP. But you know what, I thought, I'm not just going to tell you memorize that question. You should have at least an introduction to BGP. BGP is covered very heavily in the CCNP course, but it was never covered in CCNA. So I thought, you know what, I'm going to add 20 slides about BGP because I think it's important for you guys to know it, okay? So what is an attribute? It describes the characteristics of a prefix. Okay, well, what the hell is a prefix? A prefix is a network. In BGP, when you hear the term prefix, think of a destination network. Okay? Now, attributes are simply characteristics of a route. And like I said, there are many, many different attributes. Some are called transitive, some are non-transitive, some are mandatory, some are discretionary. We're going to learn what all that means as well. But, you know, you have to take off your IGP thinking caps here because BGP is nothing like an IGP routing protocol. As we keep going through all these chapters, or this chapter, you'll start to realize that how true that really is, okay? So BGP sends updates. Now we know what an update is, right? What is an update? We've already seen link state updates with OSPF, and we've seen updates with EIGRP. What do you think an update is? It's routing information, right? An update is simply me sending out routing information. So that does occur in BGP. In fact, one of the BGP message types is an update. All right, but contained within that update are prefixes with path attributes. Path attributes are used by BGP to pick a route to a destination. Very similar to a metric in OSPF and EIGRP to find the best route. But path attributes are not a metric. There are 4 categories of a path attribute. None of this stuff you guys need to know for the exam. This is purely for your enjoyment. All right? There is an attribute category called well-known mandatory. This attribute must exist in a BGP update. If you do not have this attribute in a BGP update, then an error occurs and the BGP peering session stops. Okay? So some attributes in BGP are called well-known mandatory attributes. The AAS Path attribute, for example, is a well-known mandatory attribute. Then we have this attribute type called well-known discretionary. This attribute must be recognized by all BGP implementations, but does not have to be included in an update. That's what well-known means. Everybody needs to understand the attribute, but discretionary means you may or may not decide to share that information. All right? So well-known mandatory, there's probably about 3 or 4 attributes that are well-known mandatory. There's probably about 3 or 4 attributes that are well-known discretionary. Optional transitive versus optional non-transitive. Optional transitive. If the attribute is not recognized by BGP implementations, but the transitive flag is set, the attribute is accepted and passed along to other peers. Okay, so what does that mean? It means that I don't know what that attribute is. It's an optional attribute, right? It's an optional attribute, which is really just a well-known well, actually optional is not well-known. Optional means you may or may not know it. So let's say it is an optional attribute and I don't know what it is. If it's transitive, that means even though I don't know what it is, somebody past me might know what it is, so pass that attribute along the line to my next neighbor. Because my next neighbor may choose to use that attribute even though I have chosen not to use that attribute. Does that make sense? Optional non-transitive means if I don't recognize the attribute and the transitive flag is not set, then I simply ignore the attribute and I don't pass it on to my peer. On its face, do you guys at least understand these definitions? Now, the saving grace here is that you don't have to know this stuff for the test, okay? But if you're interested in learning about BGP, this is one of those fundamental concepts that you have to understand. So let's start to look at some of those attributes. The first attribute we're going to look at is the AAS Path attribute. This is defined as a well-known mandatory attribute. Now, what does that mean? This is a well-known mandatory attribute. Every BGP router has to use this attribute. And if this attribute is not included in the update, then the update is going to be ignored. In other words, every BGP router knows what this attribute is. You can pretty much think of the AAS Path attribute as a hop count. Now see, this is the other thing that's unique about BGP. All of these clouds that you see here, there are a bunch of routers inside these clouds. We'll make it look like a little cookie here. There are a bunch of routers inside these clouds. But those routers are not running BGP. Those routers are running an IGP. The cloud itself is running BGP. It's very, very strange. It's a unique concept that you really have to get used to when you start dealing with BGP. All right? So there might be an edge router here running BGP, and there might be an edge router here running BGP. Those routers are peers. But none of these routers in the middle are running BGP. See, that's the other thing that's unique about BGP is BGP peering relationships or neighbor relationships are virtual. They're not physical. So because this router is running BGP and it's sharing routes with this router running BGP, this becomes a BGP AS. Now the AAS Path attribute is essentially how many autonomous systems do I have to go through to reach a destination? How many autonomous systems do I have to go through to reach a destination? So if you look at AS 500, for example, if there is a BGP router inside of AS 500, and that BGP router wants to reach the 180.10 subnet, it has to go through AS 300, then it has to go to AS 200, then it has to go to AS 100. Makes sense, right? That is what the AAS Path attribute is. Which ASs do I have to go through to get to that destination? Now, if I go back to the very first slide, not the very first one, but this one right here. Now you know what AAS Path is. To get to the 11 network, all right, I have to go to AS 65,000, AS 1, AS 33, 33, 33, AS 10, AS 200, AS 44. Make sense?
Within that cloud, there are EIGRP routers. And
they could be EIGRP, OSPF, whatever. Yeah.
Will those, if it's an EIGRP router, can you still do a show BGP all some, and they'll get BGP information because it's in a BGP
No.
AS?
No, you'll only get, see, that's the other thing you have to think about here, guys. BGP is an overlay on top of IGP. When I say IGP, I'm talking about EIGRP or OSPF. The routers that are inside the cloud may or may not be running BGP. They usually should not be running BGP. Only the routers on the edge should be running BGP. So the routers internally, they don't have any idea that BGP is even happening. So show IP BGP sum is only going to work on routers that are running BGP. It's not going to work on EIGRP routers.
So what would a router be if you're able to do a show IP EIGRP neighbor and you see your neighbors and you show a BGP all sum and you see BGP information? What kind of a router is that?
It's a router that's running both protocols.
Is it just a normal, there's no special thing about it, just the way it's configured and that's...
It's just the way it's configured. It's a router running both protocols, and most likely it's doing redistribution from BGP into EIGRP and vice versa. But it's just a router running both protocols. Now we have a question here online from Fabio. BGP virtual pairing is injected through internal non-BGP internal routers. I wouldn't say that the term should be injected. When two BGP routers pair with each other, they do peer, and we call it peering, not pairing, but when two BGP routers peer with each other, they just have to have reachability to each other. So as that cookie design that I drew up there where I had a bunch of routers inside and the two edge routers, those two edge routers had reachability to each other through the use of the IGP protocol. There are IP addresses on the BGP routers that we peer with, and those IP addresses are reachable because of the IGP protocol. That's why you have to think of BGP as like an overlay. BGP is kind of a transparency that you sit on top of your IGP protocol. Okay? Just think of your IGP as your way of reaching your BGP peers. It could be static routes, it could be OSPF, it could be RIP, it could be EIGRP. There just has to be some way for one BGP peer to be able to see the other BGP peer. So it's almost like the BGP routers are hosts inside that IGP network. Okay? So the first, this is the most common attribute, by the way, AAS Path. It is the sequence of ASs that we have to traverse to get to a destination. All right. Now, there's a loop detection feature that allows us to analyze the AAS Path attribute to see if the autonomous system number of my local AS shows up in the AAS Path. If 500 were to show up in this AAS Path, that would indicate obviously that there's some sort of loop. And that's not allowed, right? So the loop prevention method is to ensure that the local AS does not show up in the AAS Path attribute. Look at AS 400, for example. If I want to get to the 180 subnet, I go to 300, I go to 200, I go to 100. If I want to get to the 170 subnet, I go to 300 and I go to 200. I would not want to see 400 in my list because that means I'm going through myself to get to the same destination. Of course, there are some mechanisms in place to prevent that from happening. Keep in mind, guys, the goal of this chapter is not for you guys to be able to all of a sudden go out and configure BGP. The goal of this chapter is simply to give you some exposure to BGP concepts, okay?
Because realistically, you have to be like a senior engineer because the network is not really that big.
Yeah, BGP is a very, very complicated protocol. You can take an entire 5-day class on BGP. Of course, you can take a 5-day class on any of these routing protocols, but the goal of this chapter is just to give you an idea of what to think about when you're thinking about BGP. all right? It's a very, very complex routing protocol.
For the ASs, does that have any relation to, like, it would be a region, or it could just be,
Typically an AS, if you're thinking about it from the internet perspective, an AS is a service provider's network. It's not a region, it's an entire service provider's network. AT&T has an autonomous system. Now, they might have multiple ASs. And those ASs might be divided into regions, like Europe and Asia and North America, or whatever. We're talking about very large geographical areas, right? Hello? Okay, another attribute is called the next hop attribute. This is also a well-known mandatory attribute. Okay? All right? Essentially, the next hop is exactly what you would expect it to be. It's what address do I use to get to a destination? All right? Now, there are a couple of bullet points I want to point out here. The next hop to reach a network. So if you look at from the router that's connected to AS300, from its perspective, to get to the 150 subnet, where do I go? I go to 150.10.1.1. That makes sense, right? That's how you would expect the next hop attribute to work. It says it's usually a local network in an eBGP session. Now, we don't know what an eBGP session is yet. We're going to look at that in the next couple of slides. Well, I guess I can kind of tell you what it is. eBGP sessions are sessions between routers that are in different autonomous systems. AS300, AS200, those two routers are eBGP peers because they're peering in different autonomous systems. All right? What do they mean by the IGP should carry the route to the next hop? It means that within the cloud, the interior protocol should route the traffic to that destination. BGP is not used within the cloud. BGP is used to get from cloud to cloud. So you have to imagine that within each of these clouds, we have an internal routing process taking place. AT&T doesn't run BGP inside their network. AT&T runs an IGP inside their network, most likely ISIS. Uplinks BGP from actual physical topology. What are they trying to say there? What was I trying to say there? Because I put this in here. Uplinks BGP from actual physical topology. Oh, unlinks, excuse me. I guess that's directly related to what I was saying about these virtual peering relationships. The 150.10 subnet might be an individual network within this cloud. This router at AS300 says, hey, if I want to get to that network, send it to this next hop, which is another BGP router. But this BGP router, the one on the left, connected to AS200, is not only running BGP, but it's also running an IGP. So once it gets to this edge router, the traffic then gets routed into the cloud using the IGP. All right? Allows IGP to make intelligent forwarding decisions. All right. We'll see more of that as we get into the design a little bit later on. There's a couple of design scenarios that we're going to take a look at. All right?
Since you obviously design networks, which protocol are you using the most?
Geez, that's a good question. I prefer EIGRP, but I configure OSPF much more often because OSPF can run on multiple routers, multiple vendors. EIGRP, even though it is an open standard, it's still kind of limited to Cisco because vendors still haven't chosen to add it to their code. Right? But if a customer comes to me and says, hey, I want you to set up our network and set up a routing protocol, I'll set up EIGRP. All right. We'll pause here, okay, since lunch is here. Same time, same channel, 1:30, okay? Study your questions when we come back from lunch.